Hello everybody. We are going to solve one more problem here, which is going to be very useful for two important reasons. And I'm going to go through the problem, and then we will discuss these two reasons while we are going through the problem. So we have here 15 kilomoles per minute of air that's cooled from 430 degrees Celsius to 100 degrees Celsius. And we want to calculate the required heat removal rate, how much heat we are going to remove in order for this air to cool down from 430 to 100 degrees Celsius in kilowatts. And we have two options or two ways to do this. The first is using the heat capacity formulas in table B2, which are the constants that we have been using since 2 or 3 videos. And the specific enthalpies from table B8. So let's go through the first case first, and then we will go through the second and discuss it in more details. So this is air. We know air is a mixture of oxygen and nitrogen, and we haven't dealt with any mixtures till now. But actually air, because air is like water, it's a very commonly used material. It's already available. We deal with it a lot. So we have already data about the steam, about air. So we know T1 is 130, T2 is 100 degrees Celsius, and the equation would be Q equals delta H. We have no change in kinetic energy or potential energy, or we will ignore this. And we have no work because it's just cooling. So it's going to end up to be this simple formula, the molar flow rate multiplied by delta H. We know the molar flow rate already, it's given, and now we need to get the change in enthalpy. So the change in enthalpy is going to be got from the first case is using the CP, and the CP constants are already in the table. One of the things that you might not be aware of is that there is part of the table, or there are two rows that are only for air. It doesn't go through the details of the air, so we don't have any molecular formula of the air, but it gives us the properties for, or the CP constants for the gas phase using formula number 1. One is in Celsius and the other is in Kelvin, so you have the freedom to use any of them, given that you use the right units. And we have the constant. So this is for air. Okay, so in this case you don't need to go through the details of oxygen, nitrogen, and the components of the air. This is air, so you use the constants as they are. So this is going to be a very straightforward calculation. It's similar to what we did last time. You do the integration of Cp dt from T1 to T2. This is wrong. It should be from 400. This is right. This should be flipped. I'll correct this, but this needs to be flipped. So from 430 to 100, and this is A, and of course I multiplied A by 10 power minus 3, B by times 10 power minus 5, negative 8, negative 12, and these are the numbers. Integration is going to be very straightforward. Substituting with the limits of integration, finally we can get delta H is negative 10 kilojoules per mole. Then we can substitute here. Keep in mind this is kilojoules per mole, and this is kilojoule, and this is kilomole per minute. So we need to unify the units. So I multiply the flow rate times 10 power 3 to make it in moles per minute. So the mole will cancel this mole, and the result would be in kilowatt. So this is negative 2500 kilowatt. So it's very straightforward. There is no tricks here. It's very simple. So this is the first option. The second option is using tables. This table is already in the textbook. Let me put it here. So this table is already calculated values for enthalpies using reference pressure 1 atmosphere, reference temperature 25 degrees Celsius, and this is for some gases. This is already calculated, so you don't need to recalculate them yourself. By doing this, you can go directly to the table, pick the values. This is important to notice here that the reference temperature is 25 degrees Celsius. It's not going to be very important now, not critical now, but it's going to be very important in chapter 9, the last chapter, when we deal with reactive systems. This is going to be very important. So just keep this in mind. So we can directly go to this table and pick the values for H1 and H2 and substitute in the equation. It's going to be as simple as this. We have already data for air, so we can directly go to air. But before we skip this or go to the picking numbers from the table, just to give you an idea how these numbers were obtained. These numbers were obtained by doing the integration of CPDT from 25 degrees Celsius to the temperatures that we have here. We have like a wide range of temperatures, so this is just like this. And this is something we can reproduce by ourselves, and this is something inshallah we'll discuss next video. I'll show you how you can do this using Microsoft Excel, and you can even do this for more materials. You'll get exactly the same numbers, and you can do this for more numbers. For example, here we have the increment is 100 degrees Celsius. You can make it 50, you can make it 10, as you like. But this is how the numbers are produced. This is the message that I want to make here. So let's go back to the problem. So we have here the table. We have data for air. The integration, as we said, T1 is 430, T2 is 100. So I want to get the enthalpies for these two temperatures. So the enthalpy for air at 100 degrees Celsius is already given. It's 2.19. For table, for 130 it's not there. We have 400 and 500, so we can do interpolation. By interpolation, you can get the value. We have already done this before, so I'm not going to go into the details of interpolation. So it's going to be 12.186. And by doing this, you can do the integration. Do the substitution of H2 minus H1. This is going to give us negative 9.996. If you check what we got last time, it was negative 10. So it's almost the same. It's almost the same result that we got last time. And then you can substitute, multiply by the molar flow rate. It's exactly the same thing. You can get it in kilojoules per minute. You can convert this into kilojoules per second, which is kilowatt, which is negative 2,500, which is almost the same. Last time it was 2,500. This is 2,499, which is almost the exact same number. So the result is the same. So the two main useful information that we got from this problem is, first, we know the tables. This is going to be a very helpful resource in case you want to get the enthalpies. It's like steam table, but for these materials, for specific temperatures and specific materials, so or specific compounds. So it's going to be very helpful in case you have one of these compounds that you're dealing with in this in your problems. It's important to notice that the reference temperature is 25 degrees Celsius. Again, this will be very important next video, or next chapter. The second thing, which is a very important thing that we mentioned before and we highlighted many times before, regarding the reference state. In this solution that we did here, we said that the reference state is T1, which is 430 degrees Celsius. And we have discussed this in the previous problem. Is when we do the integration from T1 to T2, then you set your reference state to be T1. So this is the reference state. And in this case, the reference state was 25 degrees Celsius. And no matter what the reference state that we chose, the result is the same. So this is confirming what we mentioned before, that you don't need to think a lot about the reference state or to worry if the reference state that you choose will change the value of delta H. The value of H1 and H2 will be different, but the delta H is the same. And this is what we saw here. In this case, we have 2.19, negative 12.186. In the previous case, H1 is 0 and H2 is negative 10. So this is why it's important to keep this in mind, that the reference state doesn't matter. And this I'm glad that we did this problem, because the reference state, we mentioned this before about the reference state has no effect on the value of delta H, but now we can see this practically using the two cases that we solved here. Next video, I'll show you using Excel, Microsoft Excel, how you can reproduce this table and make even more data out of this. And then we will continue talking about the enthalpies for mixtures and we're getting really close to getting this part done. So see you next time, inshallah. Goodbye.